Hi everyone. This video is concerning an introduction to kinetics. For the first semester of general chemistry, we focus on reactions that happen rather quickly, right? When we go in the lab, we put some aluminum foil in some copper chloride and immediately we start to see a visible reaction occurring. It turns out that most reactions occur over a period of time, and it is important for manipulating reactions to know how fast those reactions happen. There's two ways that we think about this. One is the average rate. And the average rate is kind of the total time it takes for a reaction to happen. I'm getting ahead of myself. Think of it as moles consumed divided by the total time it takes for that reaction to happen. And honestly, this isn't all that useful because it doesn't provide us a lot of information about the details of the reaction. We can get much more information from something called the instantaneous rate. The instantaneous rate is actually a calculus concept, and if you haven't had calculus, don't worry about it. I'm going to show you a way to do this without doing any calculus, but you can think of it as if you have had calculus, it is the derivative with respect to time of the concentration of something. I do want to mention, when we put brackets around something like this, we read this as the concentration of substance A. And we mean that to be in molarity. All right. So that is, this bracket notation is an abbreviation that we're going to use quite a lot coming up. So I want to bring that up now. But really, this instantaneous rate is what we're going to calculate here in just a minute. The difference between average rate and instantaneous rate is you can think of average rate as how long does it take you to drive from your home to campus divided by the distance from your home to campus divided by the total time. All right. Your instantaneous rate is whatever your speed is in your car at any moment. So at any moment, you may be driving 40 miles an hour, or if you get to a stoplight, you're driving 0 miles an hour. Each of those is your instantaneous rate at that moment, okay? So instantaneous rate is at a given moment, average rate is over the whole period. We're not really going to think about average rate very much at all because, like I said, it's not that helpful. I'm sure my chemical engineering friends hate it when I say that, but we're going to focus on the instantaneous rate because it's actually going to give us quite a bit of information later on about how the reaction's taking place. Okay, so the way we think about instantaneous rate is we usually look at graphs such as this one. So this is two experiments, one with, this is a reaction between crystal violet and sodium hydroxide, and we do this a lot as a demo in class as well as in the lab. If you haven't seen this one, you'll get to play with it in lab at some point, I'm quite sure. And so imagine that we've done this experiment twice. We've mixed the crystal violet with a low concentration of sodium hydroxide and then a second time with a high concentration. And as you can see here, the low concentration goes down pretty slowly and the high concentration goes down much faster. So when this reaction happens, the crystal violet reacts with the sodium hydroxide. It goes from dark purple, as the name implies, to kind of a clear, a colorless solution. So this decreasing concentration here indicates that it's that crystal violet's getting used up by the sodium hydroxide. Okay, and it's happening faster for the high concentration than for the low concentration. The way we're going to quantify this, the way we're going to change this into a numerical value, is we're going to do something called drawing a tangent line. Okay, so a tangent line is one that just touches a curve at one point. Okay, so for example, if I were to look at the low concentration experiment at 100 seconds, and let's say I wanted to know what the rate of the reaction was at that time. Okay, so what I would do is I would sketch a line off of that. Okay, and I'm going to say that I'm going to try to draw a better line here. So I'm going to use my program that does this for me. And I'm not quite happy with that. Okay, I'm going to delete that. Try again. No, come on. Stop it. So let's try this one more time. It usually takes a couple times. This is a lot easier with a ruler. Okay, so and you know, if you've just discovered this video somewhere on the internet, you know, you'll have to ask your instructor. If you're in my class, I'm going to provide you with a ruler on an exam anytime you have to do this. Okay, so this isn't the best possible line of all time, but this is pretty good. So notice that this line touches the curve at one point, and one point only. And you could argue maybe it's a little further off, but we're going to call it close enough to 100. All right. And we're going to ask ourselves, what's the slope of that line? The slope of the line, the slope of the tangent line, and let's actually write that out. Slope of the tangent line is equal to the instantaneous rate at that time. And in this case, at 100 seconds, because that's where it touches the curve. All right? Okay, now, so this requires you to do a little bit of algebra, which you may have forgotten from way back whenever you took algebra. Remember that the slope of a line, we usually call that m, and we usually do that by finding 2 points and applying the equation delta y over delta x. Delta y over delta x, remember, means y2 minus y1 over x2 minus x1. And let's do an example so we remember what that means. So notice that here, it's I'm going to take this as one of my points on my line, and I'm going to call that 160, comma 0, right? Because we went to the right 160, and we went up and down 0. Yes? And then, again, I like to pick these ones on the axis because one of them ends up being 0. You could pick any point along this line, and that would be fine, okay? But I'm going to pick, this is another one of my points, and this is, I went left and right 0, and I went up 0.40, right? So those are my 2 points. So this first one, I'm going to call this ordered pair x1, y1, this second ordered pair x2, y2. And now I just take everything and plug it in, right? So y2 is 0 minus y1, 0.40. And then I'm going to do x2, 160, minus x1, which is 0. Oh, and I made a mistake here, by the way. So this is a downward sloping line. So we want the, so this is going to give us a negative number, but we're going to flip that into a positive number. Actually, we'll do that here in just a second. Okay. Don't listen to me. Okay. Do listen to me. Don't listen to what I just said. Okay. So this is going to be 0.40 over 160. All right. We're going to break out our calculator for this, just to make sure that I don't do it wrong in my head. Okay, good. I was about to do that wrong in my head. That is 0.0025 is the slope of that line. Now let's think about units for a second. Notice that my y units here are mole per liter, which I'm going to abbreviate as molar. My x units here are seconds. All right. So the units of the slope are going to be molar over seconds, right? Because I'm just doing the y unit divided by the x unit, because the slope is the change in y, which is molarity, over the change in x, which is in seconds. All right. So anyway, what have I got here? This is technically negative here, but we're gonna say that the negative of the slope is equal to a constant we're going to call k. K is going to be called the rate constant, and there's going to be a lot of things called rate something or other in this. So the instantaneous rate is the slope of the line. The slope of the line is, excuse me, I'm screwing this all up, guys. This is the rate. This is not the rate constant. I'm thinking of the next lesson. I'm really sorry. Okay, this is the rate at 100 seconds. Okay, so that's, so we're done, and I'm going to be quiet because I'm just making it worse. Okay, so we're going to do the slope of a line tomorrow, or in the next lesson. That is something else. You don't need to worry about it right now. Okay, so key thing here, draw a tangent line. It touches the curve at one point. Take 2 points on that line, figure out what they are, plug them into the delta y equals delta y over delta x equation. That's going to give you the rate of the reaction at that point in time. All right? Okay, what I want you to do is practice using tangent lines, calculate the instantaneous rate for this experiment at 50 seconds for the high concentration in experiment 1 and the low concentration, experiment, and, this is an ampersand, at 50 seconds for the low. So notice that back up here on my graph, and here I'm going to clean this up a little bit for you. So notice here on my graph that, that we've got two experiments graphed, right? And this light blue one here is the low concentration, and this black circles are the high concentration. And so at time 50 for each of those, I want you to find the instantaneous rate. All right. So go ahead and pause the reaction. The best thing to do is to get a ruler out and hold it against your screen if you have one. But any straight edge will work as long as it's going to help you figure out where the tangent line lies and figure out 2 points on that line. All right? Okay, go ahead. Okay, hopefully you've had a chance to do that. So what we're going to do, and I'm going to do it on this screen because I've got the graph on this screen. We're going to find the slope of the tangent line at 50 for both. I did say 50, right? Now I'm paranoid. I'm going to make another mistake. Okay, at 50. So I'm just going to jot this one because my little line maker on here is not so great. Okay, so there's my first line for that's the tangent line for the high concentration. And then the low concentration, it's going to look kind of like that. And if you get slightly different points, it's fine. It's an experimental error that is inherent in doing this. And you're going to get a little different answer depending on how you drew your lines and how you assign your points. And it's fine. Okay, so let's do the high concentration first. Okay, so we're going to do the rate is equal to delta y over delta x. So I'm going to call this. I'm going to use this point, and I'm going to call it. What are we going to call that? Like 85, 0. And we're going to call this point up here 0, 0.55. Sure, why not? All right, so y2 minus y1 over x2 minus x1. All right. And it's a downward sloping line, but we know we want our rate to be positive. So we're going to ignore the fact that this gives us a negative number. Some textbooks will say rate equals the negative of this. You could also think of it as the absolute value. Either way is fine. Okay. All right. That's going to give me 0.0065, and that's molar per second. All right. So that's my rate for the high reaction, concentration reaction. For the low concentration reaction, let's see. We're going to call this data point here, 110, 0. And this one over here, we're going to call 0.75. Okay, and again, if you assign these a little differently than me, that's okay. All right, so it's going to be 0 minus 0.75 over 110 minus 0. We're going to crunch that. So that's going to give us 0.0068. All right. So very little difference in the rates that we calculated for these. We would expect the high one to be a little higher in rate. But again, there's quite a bit of error involved in this because it depends on exactly where you pick your points. So we're gonna call that good. Okay. So you get a bigger difference in the rate earlier in the reaction than you do later on anyway. So I'm not super surprised by that. So key thing here is find the tangent line that touches the curve at one point. Whatever that point is, that's the point where you're finding the rate. Take 2 points on the curve, assign those, plug them into delta y over delta x. That's going to give you the instantaneous rate at that point in time for that reaction. Okay? All right. Questions, drop those in the comments. Get in touch. Hope this was helpful. Thanks for watching.